Okay, we're going to finish out this section here by talking about ping and traceroute and how they work in MPLS environments. Now, in an MPLS environment, regular old ping, or what I call classic ping, works fine, but it does have some challenges. First of all, it's only going to verify that IP routing is working, but it doesn't really do anything to verify that the end-to-end LSP is functional. The reason this is because if for whatever reason the LSP breaks, okay, the router can fall back to say, if I don't have label information to forward this stuff, fall back to the IP routing table. So even though the MPLS side of the network could be broken, it could fall back to that IP routing and still make the ping successful, which is a little bit deceiving. So if an end-to-end ping fails, it's really kind of unclear where the problem is. Is it a problem with the MPLS network, or is it a problem with maybe the customer infrastructure, right? Let's say CE1 tries to ping CE2 and it fails. We don't really know if it's because the LSP is broken in the MPLS network, or maybe because, there's a firewall in front of CE2 that's blocking it. Makes it a little bit unclear. So to kind of work around these issues, they came up with something called MPLS Ping, which is a separate utility altogether. It can only be run on MPLS routers, LSRs, and it's actually designed to verify the end-to-end MPLS LSP. Okay, so what this does is when it generates the ICMP packet and puts it inside the IP packet, that IP packet that's generated is generated with some safeguards, so that if the LSP is broken, that underlying IP packet will never be routed. So in other words, if I'm on an LSR and I do an MPLS ping, right, I'm generating an IP packet that's then put inside an MPLS packet. The way this works is that underlying IP packet, we set the TTL in there to 1, which means it's not routable. The destination IP address is set to the 127/8 range, the loopback range, which is also should not be routable. The destination UDP port is set to 3503, which is a reserved UDP port. The router alert option is set in the IP header. Now in the MPLS header, the TTL is set to 255, and basically what we do is when we generate that MPLS ping, we look up the destination of the ping, we generate the full label stack, and we push that label stack onto the packet. Now if the LSP were to fail, it's not going to fall back to IP routing because the parameters we put into that IP packet, like the TTL and the reserved port and the router alert option, is not going to allow it to be routed. Now also with that MPLS ping, if the LSP does fail, then basically what can happen is we can send back an error response message back to the source router that gives us more information about why the LSP broke. So it's a lot more useful than using classic ping in your network. So now let's take a look at traceroute. Now traditional traceroute in an MPLS environment does work differently than you probably imagine it does, and it suffers from many of the same problems as classic ping, and it's not as efficient. So let's take a look at how classic traceroute works in an MPLS environment, and then you can kind of understand why they came out with MPLS traceroute. Okay, so in this case, let's say that CE1 is trying to trace to CE2 at 192.168.2.2. So the way traceroute works, right, is CE2 sends a packet destined to 192.168.2.2, and it sends it out with a TTL of 1. Okay, so it arrives there at PE1. PE1 gets the packet, it decrements the TTL to 0, and it sends back an ICMP TTL expired message back to CE1. So now CE1 knows the first hop is PE1. Now CE1 generates another packet This time it's with a TTL of 2, destined to the same place. PE1 gets it, decrements the IP TTL to 1. It now pushes label 17 onto the stack, okay, because it knows it needs label 17 to get to CE2, and it sends it towards P1. Now here's where it gets interesting. The TTL now in the MPLS header is set to 1 as well. Now P1 gets the MPLS packet, and it decrements the TTL from 1 to 0 in the MPLS header. Now in a regular IP network, P1 would simply send an ICMP TTL expired back to the source, CE1. But in this case, we're kind of stuck, because in this case, P1 has no idea about the IP route to get back to 192.168.1.1, so it can't send that TTL expired message back to the source because it doesn't have an IP route. Remember, it's based on only label information. So the way traceroute works here is P1 actually generates this ICMP TTL expired message, and instead of sending it back to the source, because it doesn't have a route for the source, it sends it forward along the original LSP towards PE2. Okay, so the actual TTL expired message, instead of going back at this point, is going forward. Okay, very bizarre. So now P1 generates that TTL expired message, sourced from its interface facing PE1, and the TTL expired message is destined back to CE1, 192.168.1.1, and it goes ahead and imposes a label for that and sends it along towards PE2. So again, it's going towards the right. Okay, what eventually happens is the TTL expired message gets all the way to CE2. CE2 then sends it back into the MPLS network, and eventually that first TTL expired message gets back to CE1. Okay, so basically the second packet went from CE1 to PE1 to P1. Instead of P1 returning the ICMP TTL expired, it sent it all the way through the original LSP to CE2. CE2 then sent it back to PE2 to P1 to PE1 to CE1. And that's just the second hop. Then the same exact thing is going to happen to figure out the third hop, PE2. So you can see this is very inefficient and kind of quirky. Okay, there's several problems here. First of all, if the LSP is broken, traceroute inside the MPLS network might still work and give us a false sense of security because of the same reason with classic ping. It could fall back to IP routing. Secondly, if we trace from one customer device to another, like CE1 to CE2, there's no way to detect where the LSP broke because the ICMP responses are traveling along this original LSP first. Okay, so the trace route's going to break at the first PE router. So basically what they did is they invented a new MPLS traceroute utility, and basically it uses MPLS Ping in the background, as we previously talked about. The MPLS traceroute can be run on an MPLS router only, and it checks the entire path, so it checks the actual LSP. And it does this by sending a series of MPLS pings, or echo packets, that are fully labeled. So it solves those problems. That's basically MPLS Ping and MPLS traceroute. Thanks for watching, everyone. Until next time, keep studying hard, and we'll dig in here to how to actually configure and verify basic MPLS forwarding in the next module.